Hey y'all, thanks for coming to see me. This is DevOps Patterns and Antipatterns for continuous software updates. A little bit about me first. My name is Kat Cosgrove, and I'm a developer advocate at JFrog. Before that, I was an engineer on the IoT team here, and if you want to get a hold of me, I am on Twitter at Dixie3Flatline, or you can just shoot me an email. Twitter is faster though. I am not on that zero inbox technology, so if you try to email me, my apologies in advance. Slides will be up after KubeCon is over at jfrog.com/show notes. Before we start talking about continuous updates, I would like us to think about some things that we take for granted. First, why do we update software at all? Obviously, there's some software that doesn't really require updates. For example, BC. It's a command line calculator. You type 2 plus 2 and you get 4. This kind of software is not updated very frequently, as you can see here. Frankly, I am not sure what these updates were, but you can see that it hasn't been updated for 20 years, and that's probably okay. This is an exception though. Most software is updated, and it's updated frequently for a lot of different reasons. The first reason software is updated is simply us. We're users and we want shiny new features. Lots of them. We are super greedy. We want them frequently. We want them now. Yesterday is better, honestly, if I could get it. You might relate to this a little bit if you had a phone back in the 90s, one of those Nokias with Snake. If you didn't have the one with Snake, you couldn't just install it. You had to buy a whole new phone. There were even special data cables that you needed in order to move your contacts over to the new device. We didn't get smartphones until the 2000s, and the early ones were still really clunky about updates and moving data from one phone to the next. I remember having to buy a data cable to move over from a Samsung Galaxy to the Pixel 2. And silent app updates are also relatively new. This transition was driven entirely by users. The second reason we want updates is security. Old software is really dangerous. A bad breach is kind of becoming the digital version of an oil spill. It can be extremely destructive. Think of it like stopping distances when you're learning how to drive. Two components make up the stopping distance. Your thinking distance, or the time it takes you to recognize that there's a problem and react to it by slamming on the brakes, and the actual braking distance, which is the time it takes to stop the car once you've reacted and hit the brake pedal. To reduce the stopping distance, you have to reduce both components. Better materials to make better brake pads, better pavement, more advanced tires, and to reduce the thinking distance, that's a little bit harder. We eventually just have to replace human drivers with self-driving cars or some kind of like semi-intelligent autopilot to react much faster. It's similar with security vulnerabilities. There's the time it takes to identify that a problem exists, the time it takes to fix it, which is often just updating your dependencies, and the time it takes to deploy the fix. This is where continuous updates become a big deal, because the faster you can update, the better off you'll be. A couple of examples. You might remember about 3 years ago, there was an exploit that effectively shut down hospitals in the UK after ransomware took over their networks. It was identified immediately, which is great, but the fix was upgrading the operating systems. Now, these hospitals were still using Windows XP, which had reached its end of life by then and was no longer being supported with security updates. So the ransomware was able to take advantage of an unpatched flaw and completely take over. It took literally years to deploy the fix in this case, upgrading every single computer in every hospital from Windows XP to something a little bit more modern. Another example you almost certainly remember is the Equifax scandal, because we're still feeling the effects of that one today and probably will be for a while. Attackers used a vulnerability in an old version of a package called Struts. This had actually been present for months, though it was unexploited. It took them 2 months to find and upgrade all usages of the vulnerable version and deploy the fix. And I know we're only talking about vulnerabilities in enterprise environments, and they're going to be slower to update just like by their very nature. And you can say, well, in our environment, This isn't the case. We're young, we use all of the cool technology, we know what we're doing, we know how to update immediately, so this would never happen to us. That's great and all, but it's not really enough. Last year, Spectre and Meltdown went public. People mostly talked about Meltdown because like 10 lines of JavaScript could expose passwords from different parts of memory, and that's terrifying, but I would argue that Spectre is the more dangerous of the two. The problem with Spectre is that while most malware exploits coding errors or just generally poor design, Spectre exploits good design. Its attacks work by observing how well-designed applications affect the memory and what decisions the CPU makes based on certain conditions in the code. From there, they assume that other software reasoning the same way will lead to the same decisions. The better your code is written, the more vulnerable it is to Spectre class attacks. So what are you going to do? Write bad code just to confuse speculative execution? No, that's absurd. What then? Okay, this code is vulnerable, and now it's a race against the attacker. We need to identify the problem as fast as possible, and we need to deploy the fix as fast as possible, and we need to update as fast as possible. That's what talk is all about, updating as quickly as we can. On the bright side, we're actually in surprisingly good shape when it comes to continuous updates. The State of DevOps report, which many of you may be familiar with, surveys more than 30,000 organizations annually on their practices. They're looking to measure a few different metrics: the lead time, how long it takes to go from code to production, the frequency of deployments, what percent of deployments fail and need to be rolled back, and how long it takes to recover from one of those failures. Based on those responses, organizations are grouped into categories by performance, and only about 20% of them have what would be considered elite performance. To qualify as an elite organization, you need to be able to deploy multiple times per day. These organizations are able to provide more features to users faster and to be more protected from vulnerabilities because they can deploy immediately once a problem is identified and fixed. They're also recovering from those failures more easily. In the 1990s, the concept of extreme programming was hot. Extreme programming advocated for rapid feedback, which meant releasing faster and more often. And then Scrum showed up, and it wanted to reduce cycle time to the absolute minimum. And Toyota Production Systems said to decide as late as possible and deliver as fast as possible. And then Kanban said to push smaller, more incremental changes. All of these translate to, dear God, please, please, please release faster. It is not really a new concept. So you want to update faster. Great. Cool. There's no doubt that it leads to a better, more secure product, but it can also go terribly, terribly wrong, and here's how. Our first example is, of course, Java. 3 years ago, Mark Reynolds announced that Java would be updating more often. Gone were the days where a Java update takes a year or a year and a half to release. Instead, it would be every 6 months. That was Java 8, and 5 versions have come out since then. So, how's that going? Let's look at the State of Developer Ecosystem report by JetBrains from 2019. They survey developers and look for a variety of trends, but in particular, we care about the results on which versions of Java are being used in production. 83% of people are still on Java 8, 5 versions old. Yikes. So we just made a case for faster updates. Java announced that they were going to update more frequently. Why the hell are so many people still on Java 8? To understand what happened, we need to understand how we actually decide to update. So this is how users decide how to update. Something new is available, and the user comes to a decision. Do I want it? If there's nothing interesting in it, we say no and continue on our way. If yes, we ask another question. Are there any risks? This is an easy question with things that don't matter much, like the Netflix app on your smart TV or the Twitter app on your phone. If there are risks, we don't say no immediately. We ask if we trust the update. Now, this one is a little bit harder. There aren't really a lot of companies or vendors that we just kind of blindly trust, but in the early 2010s, we did tend to blindly trust Apple, so I will use them as an example. Back then, if there was an update for macOS, you most likely just went for it, even though it should absolutely be considered a high-risk update. This isn't as true now. Most people I know waited months to upgrade to Catalina and did the same thing with High Sierra. So why don't we trust our vendors anymore? Did they forget how to do QA? We tend to get better at the things we do, so I don't know if that's the right answer. The competing hypothesis is increasing complexity. You can see here that the number of artifacts involved is growing pretty rapidly, which is making things way more complicated. Using Agile as a starting point, we see CI add a little bit of complexity, and then CD rolls up and helps us out a lot, but also adds some complexity. Infrastructure as code does the same. Microservices enter the playing field. Docker becomes a thing. Serverless enters the ring, and then the rising popularity of IoT makes things way more complex. There's another problem at play here, though. It's not just the code, it's the data. We have a lot of it. This is a prediction of the global data sphere by 2025. Now, this report is from Seagate, and obviously they have a dog in that race, but it's still. Today, we think of petabytes as a lot of data, and we're rapidly moving into exabytes and zettabytes. Right now, it's mind-boggling, but by 2025, we're looking at 175 zettabytes of data. What this means is that staging environments kind of need to die. It doesn't make economic sense anymore to replicate your production environment for staging. Big companies are already testing in production. I know it's like a meme that you should never deploy on Fridays and you should never test in production, but you can be testing in production. So data and complexity are major contributors to the issue of guaranteeing quality. What do we do about it? We have another question in our decision tree now. Can we verify that the update is going to be worth the work involved? If we can't, we just don't update. We skip that version. If we can, we have to spend time going through user acceptance testing and verification, and this is a problem for us as software providers because users do not want to deal with all of this. So we have to make sure that every update includes so many appealing features they'll be willing to deal with it. A balance has to be struck. Features that we want versus the cost of accepting the update. Can we get around this somehow? Is there like a cheat code? Does the Konami code work here? I wish it did, but it does not. We do have a cheat code though. It's auto updates. This only works for things that aren't high risk, like your browser or your Twitter app. I would wager that most of you have no idea what version of Chrome you're running. These are low risk, so they happen without notifying you. I don't know what version of Twitter is on my phone. Your phone's OS is a high risk update though. You probably do know what version of Android or iOS you're running. This one requires human intervention. So we end up back at the previous decision of, are the features worth the risk of updating? Are they worth the work? Now, let's talk about building trust. If we can get consumers to trust us again, then the issue of how to update faster kind of starts to go away. Let's talk about what could go wrong. OnHub was a router from Google, eventually Google Wi-Fi. One of the really appealing features was its self-improving system. Today, it's just an over-the-air update. It was a cool concept back then, lots of slick marketing attached to it. But one day in 2017, they released a bad update. These updates are automatic, remember, so nobody said, yes, I would like this. And for some reason, on some users, this update rolled the device back to its factory settings. Because it now doesn't have access to the internet, because it's factory, Google wasn't able to roll that update back or push a patch. Everyone affected had to run through their entire network config process again. So the problem here was that an update went catastrophically wrong in a way that prevented an over-the-air fix from reaching the device. In this example, it's not really harmful, it's kind of just a little bit inconvenient. But if you think about it, that could be really, really dangerous for some edge devices. There are devices out there in some very, very isolated places that would be expensive, impractical, or maybe outright impossible to get to. So it's not really viable. The solution here is to enable local rollbacks. You have another version of the software saved on the device and automatically roll back to it if a problem is detected. This isn't a new idea either, actually. Windows 98 could do this. If you changed your desktop resolution to something incompatible with your monitor, the whole screen would go black. As an answer to this problem, Windows would require you to confirm that you want to keep the new settings. If you didn't click yes after a certain amount of time, it would assume that you couldn't because your screen is black and you can't see anything, and revert for you. Local rollbacks today are a little bit more complicated than just remembering a previous resolution setting, obviously, but it's the same idea. So these are both IoT examples, but more things than you expect are IoT devices these days, like cars. The Jaguar I-Pace is a very beautiful, very expensive electric car. Most cars, electric or not, have multiple computers in them, and in 2019, a software problem with the braking system was found to be the cause of a regenerative braking system failure. However, Jaguars, and most cars actually, can't update over the air at all, so they had to issue a recall. Physical recalls are very expensive. You have the PR cost of issuing one to begin with, but you also have a cost in actual money to rectify the issue at hand. Even bigger problem, you can't actually force the user to do it. They have to take a day off work and drive the car into a service center and get a rental. That's a pain. So the solution here is to implement over-the-air software updates and don't rely on your users to be willing to fix it for you. Preferably continuous updates. So what is the difference between over-the-air updates and continuous over-the-air updates? Let's look at another example. One of the problems with Tesla's autopilot was phantom braking. The conditions are good, nothing's in the way or on the road, weather is nice, but out of the blue, the car slams on the brakes. It sounds like a serious problem, right? And it took a while to fix, but why? Because of this chess game update. You see here at the bottom of the update is a small text notification that this release contains minor improvements and bug fixes. That's the fix for the phantom braking. People didn't get this bug fix quickly because they waited until the chess game was ready and bundled the fix in with that. Is the chess game as important as fixing phantom braking? Kind of depends, really. If you actually have the autopilot feature and you use it, then no, it's absolutely not. Fixing the phantom brake takes priority. But if you don't have autopilot and you just really like playing chess while you wait for your car to charge, then it probably is more important than the phantom braking fix. The problem here is that if you do batch updates, features that are important to one set of users have to wait on features that are irrelevant to them, but important to a separate set of users. And that sucks. Instead, if you implement continuous updates, this problem goes away. You can deliver the features as they come out. You might ask yourself, why the hell is she talking about IoT and mobile development? I'm a cloud native developer. This is KubeCon, and we're mostly cloud native developers here. How is this relevant? The thing is, our problems as cloud native developers and software providers kind of pale in comparison to the struggles of IoT developers, and we can learn from them. They don't control the availability of the target device. They don't control the state of the target. They may not know the version of the target. They may not have access to the device. So our lives doing server-side updates are way easier than the lives of those solving problems for IoT, and yet we still manage to screw it up, like, repeatedly. This example is a little old, but it was so impactful then that it's worth mentioning now, and we can still learn from it. This is the Knight Capital disaster. Knight Capital was a trading firm that specialized in automated trading on the New York Stock Exchange. They decided to roll out a new system, and for some reason, they decided to reuse some old APIs. but some of the endpoints had changed. Somehow, one of the 8 servers was not updated. New clients sent requests, but one of those machines contained old code with an API that behaves differently. Engineers decide to roll back the working code from those 7 updated servers, increasing the load on the one server running old code. There was also no monitoring, no alerts, and no debugging, so they had to sit there trying to figure out what's going on in real time, losing money minute over minute. Over the course of the 42 minutes this was live, they lost over $400 million and went out of business as a result. Absolutely horrifying. So what could have fixed this? The problem here is that humans are just really bad at repetitive tasks. Those servers were all being updated manually, but humans get tired or bored or distracted or they're depressed or somebody's just having a bad day and they aren't working at 100%. It's normal. You can't expect anybody to be perfect all the time. So the answer is to just automate everything. Computers don't get bored. They also weren't updating frequently. Not deploying regularly makes every infrequent update feel more stressful, which humans don't really handle well, and it leads to mistakes. The answer here is to just update more frequently, get better at it. It takes practice, make it a habit. That way, the chances of you making a mistake because you're anxious go down pretty radically. Another problem is that they reused some state on the target machine. Now, this could be a good decision or a bad one. It kind of depends, but regardless, you need to know the state of the device that you're updating. Reverting an update might require reverting the state. You have to know what will happen. Cloudflare is always an outstanding example. This example is from July of 2019, but we all just went through it again this past July, almost exactly a year later. A very large portion of the internet runs on Cloudflare, so when it goes down, a lot of the internet goes with it. Cloudflare fights DDoS attacks with routing rules. These routing rules are deployed frequently to combat attacks, and in this case, a deployment of a single misconfigured rule caused the outage. And the culprit was something nobody really likes dealing with: regex. In this case, it spiked CPU usage to 100%. Their status page displayed the affected region as Earth, which is cute, but kind of a problem. The problem here was that they released a bug that affected all users. Instead, they should have released to a small number of users first. That way, if a problem occurs, you can just stop the release and either revert or patch the affected users. Your potential blast radius for a problem is radically reduced. Some problems are also really hard to trace by relying exclusively on user feedback. By and large, it is hard to get users to give you information that actually helps you nail down the problem. I'm guilty of this. You are guilty of this. We all do it. Nobody is perfect. Don't pretend you are. And the solution here is to just always implement tracing, monitoring, and logging in your services and applications so you don't have to rely on a user to find your problem for you. Next up is rollbacks. A bug fix isn't always immediate, and problems aren't always easy to solve. Meanwhile, your user is hanging out with a buggy app or device, so what do? You implement rollbacks, the ability to deploy a previous version without a delay. Not every platform supports that, though. I think neither Apple App Store nor Google Play support rollbacks. You would have to take the previous version in that case, rename it as the next version, and submit it for review again. So we need an alternative. Feature flags can help you out here. You embed 2 versions of the affected feature in the app and enable or disable them with API calls. So if a feature update causes problems for a set of users, you just use feature flags to disable it for that user. Pretty easy. Another dramatic example is MoviePass, RIP. In order to complete an app update, they shut down for several weeks. They initially didn't even say how long they were going to be shut down. And obviously, MoviePass had other problems. It arguably wasn't sustainable from the very beginning. And this probably was not their death knell, but it certainly didn't help, and it never really should have happened. We need zero time updates. If you shut down for 5 weeks to perform an update, your users are not going to wait for you. Why should they? There's no reason. It's an unreasonable ask. Instead, your updates should be small and they should be frequent. They should never, ever, ever cause downtime for the user just to put out an update. So to recap, continuous updates are frequent, automatic, tested, progressively delivered, state aware, observable, and for extra credit, support local rollbacks. Where does that put us on our decision tree? An update is available. Do we want it? Doesn't really matter if it's something low risk like a game on your phone or Twitter app. That's going to happen automatically. Otherwise, are there any high risks? If no, we update. If yes, we've implemented several layers of safety nets in case there's a problem, so we know the update is probably trustworthy. Let's just update it then. Problem solved. Nobody has to think about it. Way better that way. This has been DevOps patterns and anti-patterns for continuous software updates. I hope I was able to teach you something valuable or at least keep you entertained for a while. Again, my name is Kat Cosgrove, and thanks for having me. I hope you enjoy the rest of KubeCon, and don't hesitate to let me know if you have any questions. Once again, you can reach out to me on Twitter at Dixie3Flatline. Thank you. Bye.